We, the Indian Society of Heating, Refrigerating and Air Conditioning Engineers, ISHRAE, stand tall in the Indian industry with over 10,000 professionals as members and almost an equal number of student members. Founded in 1981 and headquartered in Delhi, we operate from chapters and sub-chapters spread all over India, bringing our entire industry together. Individuals become members of our society according to their professional and academic standings. Our roadmap of the future looks very bright, with thousands of new members joining this technical society every year and bringing in a fresh outlook to our industry intelligence. ISHRAE disseminates knowledge through its technical committees, which consists of some of the best minds of our industry. It publishes technical books, newsletters, and a prestigious journal, distributing the wealth of knowledge to all its members. Working with government departments, ISHRAE helps formalize industry codes and standards. ISHRAE promotes research by offering financial support to student members to carry out groundbreaking work in technology, systems and processes. Our educational wing, ISHRAE Institute of Excellence, organizes training programs and workshops to help members enhance their skill sets. Our specially designed certification programs under ICP, that is, ISHRAE Certified Professional, empower professionals to always be in step with the prevailing technology. Specially designed courses for technicians are offered to meet the ever-increasing demand for a skilled workforce. ISHRAE organizes exhibitions, conferences, panel discussions, and product presentations throughout the country. We organize the industry's largest international exposition in South Asia, Acrex India, to showcase the cutting-edge technology, innovation, and provide a platform for closer interactions amongst the decision makers in the industry. The Acrex exhibition is now growing from HVAC and R show into BFA, Build Fair Alliance. This brings together several allied shows connected with the building services industry, all at one location. Our chapters organize several other popular events like AgriConf in Delhi, Raycon in Kolkata, Symposia in Mumbai, TechFest in Goa, and many more. We are committed to provide training and career guidance to our student members through seminars, lectures, quiz contests and site visits. A-Quest, a prestigious quiz competition organized by ISHRAE to catalyze the transformation of the budding engineering professionals. ISHRAE provides a platform to potential employers to select student members for careers in HVAC and R industry at the ISHRAE Job Junction. Young minds are made aware of the need for saving power, clean air and sustainability. The K-12 initiative of ISHRAE focuses attention on school students' development to inculcate a scientific fervor and help develop them into responsible citizens. Speedy information is imperative to keep moving forward in this hyper-connected digital age. Searcher, A specifically designed search engine is now available, which allows access to a well-catalogued database on HVAC and building services industry with just a few clicks. ISHRAE cooperates with various national and international bodies, industry, governments, academia, think tanks to promote the concept of sustainability, environmental protection and energy efficiency and conservation to enter and explore the universe of the Indian HVAC industry. Log on to ISHRAE.in that unfolds a panorama of information. Let us engineer a sustainable future together through ISHRAE.
Comfort for an energy-efficient India. Danfoss takes immense pride in engineering better indoor comfort for an energy-efficient India. We can't help but notice the increase in the number of people in our cities. As the resilient growth continues, India's outlook needs to be understood in a comprehensive manner. It is estimated that 17 of the 20 fastest growing cities in the world between 2019 and 2035 will be from India. On the other hand, the Indian startup arena will create over 1 million direct jobs by 2025. This rapid urbanization of India is expected to result in an 11x increase in energy demand. In an increasingly urbanized country, better infrastructure becomes a basic need, not a luxury. With the urban population set to grow and account for 60% of the total population, India is poised to have 41 megacities, each with over 10 million inhabitants by 2030. An increase in population has always led to an increase in pollution. 15 of the world's top 20 cities with the highest PM 2.5 are in India, and 35 Indian cities have air quality figures above the prescribed national ambient air quality standard of 60 micrograms per meter cube. Life-threatening heat waves due to climate change and other environmental impacts in the past demonstrate the need for better indoor climate and air quality. Since 90% of our life is spent indoors, urban dwellers will need modern housing and an eco-friendly and comfortable environment. HVAC systems are currently indispensable for creating such an environment and will remain so in times to come. However, HVAC poses an immense challenge as it accounts for up to 60% of energy consumed by buildings. With the demand for HVAC set to rise 15-fold by 2050, India's electric grid is bound to get strained in the coming years. Expanding capacity to meet this demand will increase carbon dioxide emissions to the tune of around 10.1 billion tons by 2030. While HVAC poses a great challenge to India's growing urban centers, it makes for the best solution as well. To overcome the challenges of the rise in cooling demand without warming the planet further, the India Cooling Action Plan has suggested that known interventions such as Bureau of Energy Efficiency's star-labeled products can help cut down cooling energy consumption by 17% and reduce cooling-related carbon emission by 20% by 2030. Energy-efficient HVAC technologies that push the boundaries of what is possible, indigenous R&D innovation ecosystems that tailor-make solutions for retrofitting buildings with sustainable solutions can together improve indoor air quality and thermal comfort, reduce carbon footprint, and bring the India Cooling Action Plan to fruition. While Danfoss is on its mission of engineering a sustainable India, the company has been driving sustainability for 85+ years across the globe and is on track to go carbon neutral by 2030. Danfoss offers solutions to create smart buildings that are highly energy efficient, reduce emissions, and lower operating costs, thus helping India achieve its climate goals. Danfoss's future-facing HVAC solutions engineer tomorrow's smart and sustainable buildings. Danfoss helps customers reduce their energy cost and the impact on carbon footprint without compromising on the indoor comfort. Danfoss India offers a wide range of HVAC solutions for chillers, pumps, fan coil units, air handling units, and cooling towers. Danfoss Solutions empower customers by enabling buildings with intelligence for intuitive functioning. TurboCore monitors itself, captures and stores up to 17,000 data parameters, allowing users to analyze and review performance of the chiller. BLT HVAC Drive enables controlling AHUs or RTUs remotely and securely with its smart logic controller. Various control systems can access the drive to incorporate the complete AHU into the BMS or cloud for optimal performance. Novocon ABQM actuators provide real-time insight by reporting to BMS about issue locations or predicting issues likely to occur. This allows facility managers to effectively solve issues and schedule preventive maintenance, resulting in minimal downtime. Danfoss Solutions enable digitalization of various functions for seamless communication. TurboCore's digital interface provides real-time data for easy connectivity with the chiller. Turbo Tool app provides data to analyze, review, and enhance the performance of the chiller. The VLT wireless communication panel communicates with MyDrive Connect app, providing full access to the drive, making it easier to perform commissioning, operation, monitoring, and maintenance tasks, thereby enabling quick response and reducing downtime. Novocon digital IoT actuators communicate with a BMS system via BACnet or Modbus communication protocols, exchanging technical HVAC data. This provides a completely automated process for controlling, monitoring, optimizing, and maintaining HVAC operations. Danfoss Solutions further allow for precise control, providing better comfort for the occupants of the building. This is done using intuitive sensors, variable speed technology, and a hydronic system. TurboCore intuitively senses the changing occupancy levels and modulates the temperature using high-precision temperature control for better indoor comfort. The variable frequency drive varies the speed of AHU fans according to occupancy levels and helps maintain temperature, ensuring indoor comfort, while the intelligent air filter monitoring maintains high air quality at low operating costs. The ABQM controls require flow of water across terminal units such as fan coil units, equipped with an integrated differential pressure controller. It also maintains hydronic balance and precision in temperature, ensuring thermal comfort. Danfoss's smart solutions ensure substantial increments in energy efficiency for lower carbon footprint. TurboCore-powered chillers with industry-leading IPLV of 0.29 kilowatts per ton help chillers achieve 5-star rating by Bureau of Energy Efficiency, India, and 35% higher energy efficiency than conventional technology. The VLT HVAC drive achieves 98% efficiency at full load by varying motor speed according to load conditions, thereby maximizing energy efficiency. Novocon ABQM has a set of 2 temperature sensors connected to the supply and return pipes, delivering precise flow at the right time, thus saving energy costs up to 25%. Danfoss Solutions improve operational efficiency for increased savings. TurboCore's magnetic bearing technology eliminates the need for oil, resulting in reduced maintenance, lower sound levels, minimal vibrations, and higher reliability through the chiller's lifetime. The versatile and resilient VLT HVAC drive operates seamlessly in outdoor temperatures from minus 25 degrees Celsius to 50 degrees Celsius. The drive's modular design also allows for side-by-side mounting of drives, enabling easy maintenance. Novacon digital actuators allow for remote access via the BMS system, enabling continuous commissioning and predictive maintenance. This flexible system adapts to building refurbishments with no physical adjustments required. Danfoss shoulders responsibility for keeping people, products, as well as the planet cool for future generations, and has taken, in no small measure, steps towards a greener tomorrow. Strides such as strategies towards low-carbon technologies, going carbon neutral by 2030, a commitment to SBTi to reduce carbon footprint, and aligning with the United Nations Global Compact UNGC's business ambition for 1.5 degrees Celsius to limit global temperature rise to 1.5 degrees Celsius above pre-industrial levels. What's more, these actions will come together and lead this journey to a sustainable future. Danfoss takes immense pride in engineering better indoor comfort for an energy-efficient India.
Thank you, everybody. Thank you, all the panelists and all the attendees joining for this. Just a minute. Yeah, sorry. So again, thank you all the panelists and all the attendees joining for this workshop. As you know that today we are covering the topic HVAC system design for sustainability and healthcare facilities, and we have expert speaker for this, Santa Bajaj ma'am with us. This program is organized by Delhi chapter of ISHRAE, driven by Women in ISHRAE, and sponsored by Danfoss. So without further any delay, I request Zonal Chair Subha ma'am to introduce Santa Bajaj ma'am in this forum and proceed further from here. Thank you. Over to you, ma'am.
Thank you so much, Tapasji, for the introduction. It's my honor and privilege to introduce the most knowledgeable and expert HVAC professional of our industry, Ms. Samta Bajaj. Ma'am, we welcome you to this forum on behalf of Delhi chapter and Women in ISHRAE. You've been leading the banner for Women in ISHRAE for decades. So, I mean, thank you so much for that, ma'am. I'll introduce and thank you so much for all the participants who've joined in and the panelists. I'll introduce Ms. Samta Bajaj to all the participants. Ms. Bajaj is the founder and principal consultant of Envirocon Engineering Services, MEP design consultant firm. She's done her BE Mechanical from Delhi College of Engineering and ESMP from IIM Ahmedabad. She's been a women chair and CWC member of Delhi chapter ISHRAE. She has more than 32 years of experience in HVAC industry, out of which 11 years with Blue Star Limited. Thereafter, as an independent consultant with diverse experience in HVAC, system design and retrofit, hospital, commercial, residential, airport, and many more. She's worked with all leading developers of India, with DLF, Max, Healthcare, Airtel, Bharti, Reality, HSCC, Rights, Ansels, M2K, MR, MGF, name it. She's worked with all of them. She's great achievements to her life, which is she's published a lot of articles for ISHRAE journals. She's conducted workshops, training sessions at ISHRAE, at Indian Building Congress, architectural colleges, and at national events like Urja Varan on sensitive subjects like assessment and upgradation of infection transmission control in buildings, indoor air quality, sustainability challenges, way forward, smoke management systems in buildings, adaptive thermal comforts, etc. She's done immense for our industry. She's a great, knowledgeable speaker, and we are so honored to have you with us, Samta ma'am, and to enlighten us with your knowledge on HVAC system design for sustainability in healthcare facility in specific. Thank you so much, ma'am. Over to you.
Thank you so much, Sukhda, for such a kind and generous introduction. Good afternoon, everyone. First of all, I would like to thank ISHRAE Delhi chapter for giving me this opportunity to share my experience on HVAC system design for sustainability in healthcare facilities. And foremostly, I would like to thank all the participants for attending this session today. Now, sustainability is a core concept in the HVAC industry today, as environmental concerns have become challenges for the entire globe. There is a serious need to address reduction of carbon dioxide emissions and to lower the carbon footprint size. So, friends, it's known that HVAC systems are the biggest consumers of energy in a hospital building. Tabas, can I share my screen?
Yeah, ma'am, please go ahead. Please go ahead. Yeah.
Is it visible?
Yeah, ma'am, perfectly fine. Yeah.
Okay, fine. So we all know that HVAC systems are the biggest consumers of energy in a building. And that's because of high and continuous demand for most of the areas. Hospitals consume around 3 to 5 times the energy per unit area that is consumed by a typical commercial building. And if we see the distribution, HVAC alone in a hospital building consumes around 55% power. So what are the outcomes? Outcomes are increasing capital investments and operational costs, depletion of global resources, power, water, and air, detrimental effects on the environment in terms of global warming, greenhouse effect, and more carbon dioxide emissions, which all show in climate changes, natural disasters, spread of diseases, and loss of natural habitat, as we are already seeing in present times. Just to give you an example, 1 kilogram of R410A refrigerant leaking into the environment is equivalent to 2 tons of carbon dioxide emissions. So you may be amazed to know that there already has been 0.8 degrees centigrade increase in ambient temperature as compared to the end of 19th century, and a further 1.5 to 5.3 degrees centigrade is expected by end of 21st century. And at the same time, if we are a little conscious and judicious enough to try to make the system power efficient by even 10%, then for a medium-sized facility, say 4 to 5 lakh square feet, it would be equivalent to rid the environment from a potential 25,000 kg of greenhouse effect. Or you can say it is equivalent to afforestation of 750 acres of land. So that's a big figure. So friends, I think it's the right time and it's imperative now to explore threadbare all the energy conservation opportunities, and believe me, they are right there. Right from the design onwards to all the steps like installation, operation, maintenance, testing, balancing, and even the renovations. So now, where is the requirement of green hospitals? Where when we say we need to build green, again, we repeat the fact, the global facts, that already 0.8 degrees centigrade increase in temperature rise has happened and 1.5 to 5.3 is expected. So, what is going to be the impact of all this global warming? Effects are that it will cause sea levels to rise. It will cause extreme weather conditions like droughts or floods at some places. It will change the amount and pattern of precipitation. Even the nutritious value of the yield is going to come down. It will change the agricultural yield. It's going to cause melting of the glaciers. Glaciers will change their directions, expansion of the deserts in the barren, unproductive areas. Many species have already become extinct and many are on the verge of extinction. Increase in the range of diseases, as we are already seeing. So, like when we say now, as Sudha also said, like we are, and I think that Danfoss video showed that their aim is to restrict the temperature rise to 1.5 degree. What is the, like, if we compare the figure 1.5 versus 2 degrees centigrade, it's a major change in so many parameters. So this is a slide which is showing all those things. Like if we talk of 1.5 degrees centigrade, it's going to cause 100% increase in flood risk. Versus 2 degrees centigrade, it's going to increase that risk to 170%. Then the species, 6% of insects, 8% of plants, and 4% will be affected with 1.5 degrees centigrade. Whereas at the same time, rise of 0.5 degree is going to affect a higher percentage. Water availability, water is not going to be available to 350 million urban residents by 2100. And if we talk of 2 degrees centigrade, 410 million people will be affected because of the droughts. Arctic sea ice. So it's predicted as per this website, climatecrisis.net, that Arctic Ocean, it will see ice-free summers every 100 years in case the global warming is 1.5 degrees centigrade. And if it rises to 2 degrees centigrade, it will be ice-free every 10 years. 9% of the people will be exposed to extreme heat waves every 20 years in case of 1.5, and the same will be 28% in case of 2 degrees centigrade rise. Sea levels are expected to rise because of the floods, and expected sea level rise is 48 centimeter by 2100 by the end of the 21st century. And at the same time, with 2 degrees centigrade rise, it's going to affect 49 million people, with the sea levels rising to 56 centimeter. So likewise, economic growth will slow down, oceans, the marine life will be affected, coral bleaching will be affected, and the food also, every half degree warming, it will consistently lead to the lower yields, and the nutritious content in the vegetation also will come down. Then at the same time, deaths from global warming are going to double just in 25 years. These are very serious parameters. Heat waves are going to be more frequent and intense. Global sea levels could rise by more than 10-20 feet. Droughts and wildfires will be more frequent. Arctic Ocean could be ice-free in summer by 2050, and more than 1 million species worldwide could be driven to extinction by 2050. That was once again, there's some adjustment problem which is coming. I'll again try sharing the screen. Now it's okay. So when we talk of green buildings, what's the difference between a conventional building and a green building?
Ma'am, sorry.
Is it visible now? Is it visible now?
No, ma'am.
Now it's not visible.
Yeah.
Actually,
reset. Yeah.
Okay, I'll do it. Thanks. Is it okay now?
Yes, ma'am.
It's okay now, no? Okay.
Yeah.
Okay. So when we talk of green building versus a conventional building, what are the differences? Green building is the one which consumes less water, consumes less power, conserves the natural resources, and generates less waste. So this is a very common language. In very common terms, we can define a green building or a green hospital building. And what are the modes, what are the implementation and recommendations for going ahead with design of a green building? So today we are talking of net zero energy and net zero carbon buildings for sustainability. And HVAC has a major role to play in designing of NZD or NZB net zero carbon buildings. And why so? Because again, we repeat that since HVAC system, they are the largest energy consumers in a hospital building. So the technological improvements, developments in the HVAC design and systems, it will contribute to net zero energy and less carbon, net zero carbon hospital buildings. So the fact is that the average healthcare facility uses around 3 to 5 times the annual energy consumption of a typical, as compared to a typical commercial facility. And if you see the distribution, air conditioning alone is consuming 55%, whereas the other services like lighting, hot water, kitchen, they have a relatively lower contribution. Effects are basically higher capex and opex costs, higher power consumption, environmental effects, ozone depletion, global warming, greenhouse effects, and increase in the carbon footprint size. So that we have seen in the previous slides. So in this presentation, basically, I intend covering in 6 parts. First of all, we'll be discussing what are the typical healthcare HVAC requirements and constraints. Why do healthcare facilities consume so much energy? How can we design for more energy efficiency? And then we'll also be discussing the role of architects to accomplish this goal. And in present times now, there are many new technologies. So I'll be briefly touching, because it's not possible. So many technologies are there, and each and every technology is a subject on its own. So I'll be briefly touching upon for the benefit of all. And last but not the least, we'll also be discussing the opportunities of energy conservation in operation, maintenance, testing, balancing, retrofits, and renovations. So first of all, coming to the part 1, understanding healthcare HVAC requirements and constraints. So like HVAC in a healthcare facility or a hospital, it's not only for comfort only, but it's a part of major therapy. And there are specific needs to it. Also, there are psychological aspects which are related to early healing of the patient so that he can be discharged after the treatment soonest. So if we come into the details, a few parameters I will touch, like how HVAC, it's a part of major therapy. If we talk of cardiac patients or the patients with head injuries, they require cold and dehumidified type of environment for their healing, because to maintain the blood circulation, because when they are under this ailment, cardiac or with the head injuries, the body is unable to dissipate the heat released due to the metabolic activities. So the cold and humidified environment is required to ease that out. So likewise, burn patients, they require, on the contrary, warm and humid environment, which is very high temperature, 90°F and RH up to 95%. And then the patients with the respiratory pulmonary diseases, they also require warm and humid environment, because the drier, it can cause the small particles to enter into the lungs. And the cilia, which are the, the basic building blocks of the lungs, they also capture these particles. They dry out in the dry conditions. So for the patients of the pulmonary diseases, they require humid and warm climate. Likewise, the patients undergoing oxygen therapy need warm and humid, and people with the arthritis, they require warm and low RH conditions, RH less than 35%. And patients with thyroid toxicosis, they are sensitive to hot and humid conditions or heat waves, so they need a cold environment. And likewise, generally, elderly patients or people otherwise also, they are exposed to, if they are exposed to extreme heat waves or high ambient condition, it's a matter of public health threat also. So it's required air conditioning there has to take care of the optimum temperature required for the body. So from these slides, we could see that there is a variety of requirement. It's not an application where it's a single temperature or RH requirement. Different ailments, they are eased out, or the treatment becomes faster with the different types of environmental conditions. And now these were the points where the air conditioning was a requirement as a part of the major therapy. Now coming to the specific needs of air conditioning. So there it can be listed down as temperature and humidity are the requirements. Air filtration is a serious requirement. Infection control is a prime requirement in a hospital. And then there are many areas which are 24/7 operation. contaminant exhaust, because hospitals generate so many contaminants, not only because of patients are also sources. Then there are certain samples of the hot labs, laboratories, which handle the radio active substances also. And then the hospitals, they're also exposed certain areas to the hazards, because they are handling the hazardous chemicals, and at the same time the infectious patients. So there is all likelihood of transfer of infection within the hospital. And then there are a requirement of high ventilation air requirements, which are to reduce the contamination. So these are the specific needs of a hospital air conditioning. So coming briefly to each one of these, air filtration, like most of the areas, many areas require HEPA filters in a hospital. You need in operation theaters, and the MERV 13 or MERV 14 filters, that is the fine filters, are required in majority of the areas, whether it's radiology, imaging, or operation theaters also, and CSSDs. So MERV 13, 14 are a must in most of the areas. So, and when we talk of such heavy filtration, 3-level filtration, in certain cases, that means there is a lot of manpower energy which is consumed, because there's a lot of resistance to the airflow. The pre-filters, the fine filters 10 mm, and then with the HEPA filters 25 mm, and the air has to overcome all these pressures, and that means high fan energy. And then carbon filters are also used in certain areas like the kitchen, to arrest the orders, or in the other areas of the hospital where order control is required. So this is basically the table which is showing the different categories of filters that are deployed in the hospital application. We talk of the pre-filters, which come in the category of MERV 8. Then we have the fine filters in the range of 13, 14, and HEPA filters MERV 17 or MERV 18, which can capture particles of 0.3 microns with an efficiency of 99.999%. So we are talking of such heavy filtration in the hospital application. Ultimately, that means it's all adds to the fan energy consumption. Then amongst the specific needs again comes the requirement of infection control. So basically this is a hard fact that the hospitals which are meant for the treatment of the patients, they are also the sources where there is much likelihood of catching infection, and catching infection in the hospitals is not very uncommon. And patients, after having been treated in the hospital and after being released from the treatment, they within 15 days also they may show signs of some hospital acquired infection. So for that purpose, there are isolation rooms, a positive isolation room or a negative isolation room, or directional airflow or pressurization of the areas is required to prevent the infection control. And then these isolation rooms also need the HEPA filters again, and there are specific exhausts also associated. So all that are energy consumers. Specific needs also include 24/7 operation of certain areas like patient rooms or wards or ICUs. For that purpose, so many areas in the hospital, they have 24/7 requirement. And then the contaminant exhaust, as I said, there are so many sources of exhaust in a hospital. It can be isolation rooms, it can be dirty utility, it can be laboratories, hot labs. So all those require the exhaust. So that's again an energy consumer. Hazard control, you need to control the hazards, because in the lab certain radioactive compounds or the hazardous chemicals may be handled, or during the pandemic situation, you had to have several sort of separate isolation rooms. So it can be known or unknown hazards which have to be required to be controlled in a hospital. Then you have a requirement of high ventilation air. The makeup air requirement is most in the hospital applications as stipulated by ISHRAE standard 170, and that is to reduce the contamination, to drive out, to expel the contamination. So as per the latest guidelines by NABH, we require minimum 4 air changes of the fresh air for the operation theaters, and likewise for the other areas also it is normally more than the normal comfort applications. It can be 4 or 3. We are seeing this is as per IS 170. So, and the heavy filtration, all these are the lead to high system energy consumption. And the psychological requirements attached to it is that the hospitals, they need to provide a picture of health, happiness, and comfort, because that enables early healing. So it's a part of certain areas like meditation rooms and all, the recreation and meditation, they are a part of the hospital applications nowadays. And so they are also the part of the facility. So before we go further, we can briefly touch upon the hospital architecture. Like depending on the specific requirements of the function, there are different departments in a hospital. They can be classified as general surgery, can be internal medicine, it is diagnostics or radiology, OPDs, psychiatry, rehabilitation, and then it can be ophthalmology, neurology. All these areas are there which have a different like in a multi-specialty hospital, there are different small departments handling all kind of functions. And normally, if we see the layout, there will be emergency department on the ground floor. OPDs can be on the ground or on the upper floors. Patient floors are normally on the upper floors, the patient rooms floors, so that there is minimum medical intervention by the normal people, and they are slightly secluded. And if we talk of a typical healthcare organization, we have normally I have seen after having handled around 50 hospital applications, like it's the same systems. Like it's basically there are two. One is a construction and design department, and one is a maintenance and operation department. Construction and design department is headed by the architect and engineer who look after the new construction or the renovation of the existing buildings. And then the operation and maintenance heads are there who take over after the construction or renovation is over, and they operate the systems, maintain the systems, and any upgradation or repair is required, they will be taking part in those activities. Then we come to the hospital zones. Different zones in a hospital are like some areas which have around 6 to 8 hours of operation. Then there can be some areas with 9 to 14 hours of operation. Few areas are with 24/7 operation. So one is the visitor and outpatient, or normally known as OPD. So this is the outpatient wing, which will have OPD, consultant rooms will be there, clinical tests will be there, or the waiting rooms and lobbies. Then you have the radiology and imaging, where X-ray, MRI, or whatever routine tests are required, and the emergency and triage. So there the patients come and go the same day. They don't have to stay back. So this is a visitors and outpatient department. Then we have the inpatients and surgeries. So inpatient and surgeries are it's the operating rooms, and where they are preceded. Patient first goes in the pre-operative rooms, and then post the surgery he spends some time in the post-operative rooms, and first in the intensive care units, where after he recovers a bit, then they are shifted to the individual patient rooms or so. So we have in the inpatient and surgery, we have the operation theaters, we have the pre-operative, post-operative, ICUs, and then the wards in the patient rooms. So here, these are the 24/7 areas. Patient rooms, ICUs also may be 24/7, and they are 24/7, and post-operative and inpatient, they will be there, but not, they'll go with the timings of the operation theaters. Then we have the support functions like the administrative sections, laboratories, blood banks, CSSDs, pharmacies, mortuary, laundry, maintenance zones, and parkings. So these are the support functions in a hospital. Then we have interaction spaces, which can be the mini hotels, and meditation rooms are the new concepts in the modern design hospitals. And then we come to how many zones, which areas particularly require air conditioning in a hospital. Not all the areas, though they are desired, but mandatory areas which require to be air conditioned are laboratories, blood bank, CT, MRI, USG, ICUs, ICCUs, operating rooms, maternity, labor delivery rooms, CSSDs, and kitchen and laundry, these require to be spot cooled and with good exhaust systems. So these highlighted areas, here the requirement of air conditioning is essential, and at the same time for the public areas, OPDs and radiology, these areas, it is desirable. And most of the areas, and particularly in the areas where sophisticated machines are housed, it requires minimum microwave filtration. Now, coming back to the question that why do healthcare facilities consume so much energy? So here, if we see the requirements of the temperature, RH, pressure, and total air changes, then there is a lot of differences in the requirements. We talk of operation theaters. So there are 3 categories of operation theaters which have been classified as per the NABH guidelines. It is class A, which are for the highly critical organ transplant operations, and there the temperature requirement is 18 to 24 and RH is 20 to 60%. And likewise, B and C may be categorized as a general and slightly on the lesser criticality side operating rooms, and there also temperature conditions are same, 18 to 24 and 20 to 60%. Positive pressure, outdoor air changes required is 4, and the 20 air changes is the total minimum air quantity required. But the class of cleanliness in the critical, it is class 100 at the supplier grill condition, and B and C is class 1000. So that means lot of air. Class 100 at the grill condition means class 10,000 in the area when the OT is operational. So class 10,000, if we don't have to go with this figure only. For achieving this condition, you may require even more number of air changes. So likewise, there is a requirement which has been stipulated for the other areas also. So normally temperatures are 21 to 24 in the other areas, and positive pressure or negative pressure with 2 air changes of the fresh air. So how do these figures compare with the normal conventional air conditioning? In OTs, when we are talking 20 air changes, it is again 6 to 8 air changes in the normal comfort applications. And ventilation, this is the total supplier change rates. And if we talk of the minimum outdoor air ventilation, it is in OTs, it is 4 air changes minimum, as against 1 to 2 in the normal comfort applications. Now, how the number of air changes, it affects the particle removal? But because it's the solution to pollution is dilution. So the same thing goes here also. As the number of air changes increases, the time required for removal of the particles also goes on reducing. So it takes only 6 minutes. With the 50 air changes, it will take 6 minutes to remove 99% of the total, and 99.9% will be removed in 8. As the air quantity reduces, the particles get removed in a very much faster way. Then besides that, we have a requirement of humidification. The humidification, why we require humidification in certain areas? To prevent the static electricity generation, because that is detrimental to the operation of the sophisticated machines are in crores. The machines which are used in linear accelerators or MRI or X-ray or PET scans, these are very, very expensive and sophisticated machines, and they have a definite range of temperature and RH requirements which are stipulated and mandated by their manufacturers for their optimal performance. So we need to provide the humidification to maintain that range, and at the same time humidification is also required to prevent drying of the mucous membranes. That is, what happens is that at the low RH during COVID times also we learned that the low RH, it causes the particle, all the water gets dried up and the particle becomes smaller in size, and then it is easier for it to enter into the respiratory system of the person. So that means the immunity reduces. So for that purpose, you need to maintain optimal humidity in the space. Then dehumidification is a standard requirement of air conditioning. We have to control the RH, because higher RH, that will be also can be the breeding ground for the microbes, and it's also not comfortable for normal comfort conditions. Also, there is a minimum range, and for infection control and for operation of sophisticated machines, again higher RH is not, there is a range that beyond that the machines will show faulty operation. Then we already talked about the strict stringent filtration and the fan energy requirements in the fine and HEPA filters, then 24/7 operation of certain areas, so that will obviously need many HUs or fan coil units to keep running, and it will consume energy. Then we have the reheat requirements. Reheat is a parasite to energy. Reheat means, that means we are creating artificial heat to bring back the restore the overcooled condition of the air conditioned space. So this is a table which is showing the average, approximate heat generation from these hospital machines. MRI machine, it generates around 83,000 BTU per hour, and a Linac machine, it's dissipating around 1,11,238. So you can see how substantial are these figures. So what happens is that when we do the heat loads, or when we design the HVAC system for the hospitals, we base it on the equipment load dissipation from these machines in the radiology and imaging areas. Now, but the machines are not in operation all the time. When the machines are off and the process is not on, it causes that the air quantities are on the larger size than required. It causes overcooling, it causes increase in the RH. So to bring it back to the normal condition, reheat, artificial heat has to be provided. So this reheat requirement also is a major contributor to the energy consumption in the HVAC system for the hospital. Then the winter cooling requirements, the critical areas like OTs or radiology, Linac, MRI, again, the areas where the high sensible load machines are there, there you need to have the winter cooling provision, also separate chiller or a DX thing. So that is again energy consumer. And then what is my experience is that the standards may be asking for 18° or 21° in the operation theaters. But when we talk to the medical teams and the administrators, they find that the surgeons, they ask for almost cold store condition in operation theater. They want, as these are the specific requirement of the medical teams, they require 16° in the operation theaters. So we have to give a supplemental cooling also, in addition to the chilled water or whatever has been provided. We have to give a supplemental DX coil downstream of the main coil to bring the system down to 16°C, because it will not be possible with the normal chiller operating. And at the same time, there is a variety of the temperature required. Nurseries and the areas handling small children, babies, there the temperature requirement is high, 24 to 27°C. So there we may require more heating. So above all these parameters combined, they cause higher energy consumption in hospitals, which is 50 to 55% of the annual energy in a typical healthcare facility, no matter its location, whether it's in West India or North India, because it's not basically on the ambient conditions, it's more process and the internal departmental related. So if to summarize, we can see that the major energy users in hospital are the space cooling and dehumidification, space heating and humidification, outdoor air cooling and dehumidification, outdoor air heating and humidification, reheating, and the fan energy requirements. Then in hospitals, as I earlier mentioned, there are so many exhausts happening. To list them down, we can say that there have to be exhausts from kitchen, laundry, hot labs, CSSDs, isolation rooms, hazardous contaminant areas. So these are here depicted. We have in kitchen, then laundries, we have the hot labs, then we have in the CSSD, which handle the cleaning of the sterilized supply, which have to provide the sterilized supply to the entire hospital facility. Then we have to have the exhaust from the isolation rooms, from the hazardous storage areas, from the laboratories, from the waste storage rooms, from the dirty utilities, from the anesthesia stores. So all these are the exhaust which happen in the hospital facility, and they contribute to the consumption of energy. Now, in part three, we say, how can we design for more energy efficiency? This is through basically all these parameters. If we pay attention to, we go for energy efficient HVAC design, energy efficient equipment selection, energy management systems, proper operation maintenance, and during the architectural stage only, if we take care of the building envelope and plan the spaces accordingly, we can reduce the heat loads in the building. And the hospitals are one areas where, expansions and renovations are very, very common. In fact, I find that before a hospital facility is developed, I have seen in certain cases that the trends change, then they will, in the part area, some new technology, some new department will be thought over, and immediately the renovation or expansion will also start. So because the medical technology changes very, very fast. And then even in the expansions, renovations, we need to be cautious, and we can also consider retrofits, replacements for energy savings. The old systems, lighting, ducting, piping can be looked into, because everywhere there is a potential of energy saving. So how we design for more energy efficiency? So first of all, we'll just go through what has been the normal conventional system design. Normally, the air handling units are constant volume, and the cooling heating coils, they are at a fixed discharge temperature, 54, 55. Chilled water pumping is normally, condenser water pumps or primary chilled water pumps normally are constant speed. Secondary, I have seen variable since the onset of my career 30 years back. They had started at that time only, variable secondary pumping system had got introduced in the HVAC industry, and they had started going in for the variable pumping in the secondary. But now, in fact, nowadays, it is now common in the primary as well as condenser pumping also, condenser water pumping also. Cooling tower fans conventionally have been constant speed. Condenser water pumps have been constant speed. Economizer cycles, which take benefit of the outdoor air, better improved conditions, ambient conditions, they also are not normally implemented. TFA units for the patient wings, they're designed for 100% pressure, so that is a lot of energy consumer. Now, what are the various strategies by way of which we can reduce this energy consumption? We can first of all explore VAV system control to save energy, particularly in the areas where the areas are not occupied for several hours, or where some directional airflow is not required, or where the space sensible cooling airflow requirements are high. That means the areas, again, as we were discussing, imaging and diagnostics, where the machine load is very high, but the machine is not in process or not in operation all the time. So during the idling time, we can always think of reducing the airflow to reduce the fan power consumption. So then if we talk of pressurization, what does it mean? It means that how we have to maintain the pressure gradient from the cleanest to the dirtier part. And for maintaining this air pressure through pressurization, again, we need to pump in more air and more to maintain the required pressure differentials. Then if we think of considering VAV systems for the energy efficiency, then we can just have a glance of the operation of the various departments in a hospital. So ISHRAE compiled data only from there. I have picked up that most surgeries, they work occupied hours are 65, or we can, on an average, we can say 8 to 9 hours per day. Recovery areas, outpatient treatment and radiology areas, all these areas, they function only for 8 to 9 hours per day. So that means only about 30% of the hospital is constantly occupied, and even where it is constantly occupied, there also the internal loads will be fluctuating. The requirements are fluctuating frequently. And then we think of the 24/7 operation areas. So in the 24/7 operation areas are the patient rooms or ICU rooms. Patient rooms also in a facility, they will be normally 80% of the patient rooms will be normally occupied. 75% of the ICU rooms will be normally occupied. Nurse stations are normally 24/7 operated, day and night they work. And then we have the emergency rooms also. Normally they will be working 24/7. Lab areas, around 50% of the total lab areas will be working. And emergency radiology, around 15 to 25% of the areas. Emergency surgery also 15 to 25%. Autopsy, CSSD, nurseries will be working 24/7. Corridors, waiting areas, medical records, clean linen storage, of course, they have, but there is a discretion. Normally, the administrators, they switch off in the air conditioning, then its ambience are favorable in the corridors and atriums and the waiting lounges. And then the support functions or the other areas, purchasing works, but all these areas, they work for 8 to 9 hours per day. Purchasing, maintenance, X-rays, nuclear medicine, on a general OT and all these things. Then 9 to 14 areas, again, physical and occupational therapy, OPDs, laundry. So this is a distribution of how the various areas are working. Now, how we can use this fact in giving the VAV control for energy conservation. We can employ VAV control in all the areas where such variation in the load is happening and where the life cycle, of course, there is a cost to the VAVs and to the VAV system controllers and all those things. And wherever it is effective and there is a good payback, particularly in the OPDs, offices, in the pre-post operative areas, which are also not critical as regards to pressurization. There is no requirement of any directional flow or the pressurization. So there we can use VAV. Then we can, even in the areas where directional pressurization is required, still we can go for variable return air flow tracking. We can track the return air flow direction, like in ICUs and labs, and provide the VAV there also. But it's normally not recommended because if the maintenance or the operation is not proper, it may cause problems in the pressure differentials. And then the NABH also, it allows the minimum air changes. It can be reduced to 25% of the total requirement during the unoccupied periods, even in the operation theaters. So that means we only have to maintain the positive pressure, and we can reduce through the VFDs or through the controllers, we can reduce it to 25% of the rated value. And then in the areas again where the sensible load is high, like CP, MRI, LINAC, we can reduce the airflow when the load is low, when the machines are not on. So how does it happen? This is a picture which is depicting it. So if it is in the normal condition, we are supplying 20 air changes, that is 2200 CFM, and return air is 1850 CFM. That means there is a offset of 350 CFM, which is required to maintain positive pressure in the operation theater. And then in case of non-occupied area, we don't have to switch. It's not permissible to switch off the unit in the HU, because otherwise the pressurization and the sterility of the OT will be lost. So there, in that case, we can reduce the supply to 350 CFM, and then in that case, unoccupied CFM, during the unoccupied hours, the return air will be 0 CFM. So this is how the VAV control will act. And there are different approaches, different methods of achieving it. You can have a 2-position supply, shut-off damper can be there. There can be pressure-independent valves, and there can be modulating control dampers also, depending on what kind of investment and what kind of complexity in the controls we are desiring. So, like here we have in the supply also we have a DDC controller, and in the return also we have a VAV damper. So, whereas the supplier, that airflow will be, set point will be based on the occupancy, and it will be controlled by the occupancy sensor. But in case of directional control, return air flow, it will be based on the occupancy, but controlled by the space differential pressure sensor. That means as soon as the required differential pressure setting is disturbed, it will modulate the return air to bring the pressure setting back to the set value. So if we summarize that in the non-pressurization control, which are the areas which are good candidates for VAV application, we can apply them in general patient rooms, in examination rooms, dining areas, atrium, some lab spaces which are not very critical, and because some of these spaces may have minimum but no pressurization control requirement, and when some may require minimum for exhaust, because exhaust has to be made good also. And then in the clinical pressurization control areas, where we can consider it in the radiology treatment, in the procedure spaces, in the recovery, in the therapy, and bronchoscopy, endoscopy, here we can consider VAVs even with the pressurization requirements. And this is a case study which was done, and the data, without going into the details of the data, I'll just say that like the 11 notice in support, where it was the total requirement was this, and the total idling time when the system was unoccupied is almost 50%. So there was a saving in the reheat, cooling, fan energy, and heating and humidification, so that the payback was within 3.5 years. Now after that, it is a saving. Another control strategy to reduce the cooling requirement is to reset the supplier temperature to save energy. Normally what happens is we are sticking to a fixed supplier temperature, which is 54, 55 degree Fahrenheit. But when, depending on the outside conditions, when the outside temperature comes down, it can always be raised from 55 to 60, 65 degree Fahrenheit. Also supplier temperature reset by demand and by fluctuation in the outside temperature. So how it will affect? It will reduce the requirement of cooling. It will require less chill water flow, and if the system has been designed with the air side economizer, operation of that also will be much easier, and it will reduce the reheat energy significantly. Another approach to save energy is the adaptive thermal comfort, which has been, which is a new concept and which has been also accepted and approved in the National Building Code of India and the ISHRAE guidelines everywhere. And what is this approach? This approach is basically, it says that the comfort is not a single point temperature. We cannot say we are 22, we are comfortable at 22 or 24. It relates inside temperature to outdoors. So they say that we are comfortable based on what is the temperature outside. If it was 45 degrees centigrade last week, and if it is 40 degree centigrade this week, we will always be, we'll say it's comfortable, more comfortable. So, and it also takes into consideration the factors like clothing and the activity level and the physiological thermoregulation, because the body itself, it's a heat engine and it has the potential to regulate the temperature on its own based on the changes in the ambient conditions. How does it happen? So normal comfort conditions are perceived to be 18 to 24 degrees centigrade. But like in the adaptive thermal comfort approach, it says that if we reduce the acceptance level from 90%, which is the normal definition of the thermal comfort, then the 90% people are comfortable in a room. If we can increase that band to 80 or 70% acceptance, then we can also increase this 24 ka limit to 30 degrees centigrade. And then they also say there is a magic. The air velocity is a magic. जब AC के साथ पंखा चलता है, तो we all know it is much more cooler. पर उसमें 3-4 डिग्री फ़ारेनहाइट का वैसे ही फर्क आ जाता है. So that means the comfort range can be widened from 24.7 to 31.7. So the airspeed raises the upper limit of comfort band by 1 to 2 degrees centigrade. So by increasing the air velocity, that is the adaptive thermal comfort approach. So and the physiological thermal regulation, it explains that the body is a heat engine. The core body temperature is 37 degrees centigrade, and body has the potential to regulate the its heat dissipation based on this. Kya hota hai, like if it is 37 degrees, the temperature in the ambient, it rises by 2 degrees centigrade above this. It is a cause, it's called hyperthermia. So hyperthermia mein what happens? Automatically body responds to it. The arteries expand. Why do they expand? They expand to provide more surface area for heat dissipation. The heat that has been released due to metabolic activities, it will find more area to get dissipated. Body will perspire, that will bring the cooling effect. And so that the temperature, ultimately it is brought back to the body core temperature. Similarly, when the temperature reduces below the body core temperature by 2 degrees centigrade, it is called hypothermia. Then what happens? The vascular constriction, arteries, the arteries will shrink so that there is less area for the heat dissipation. And cold shivering or the falling temperature on feet and hands, these are all which happen automatically. So how this adaptive thermal comfort, it can be a design solution for sustainability, because it can reduce the mainstream air conditioning by more than 40%. And what are the systems which go into it for adaptive thermal comfort? Instead of going for the total mechanical air conditioning based on the refrigeration machines. There are now, equipment and the technologies, which is indirect, direct evaporative cooling or the hybrid cooling. We are all familiar with the normal evaporative cooling, but it's not very effective in the monsoon season or in the areas where there is humid climate. So there is a additional, there's a improvement to that. It is the indirect evaporative cooling, where there is a no direct. There are two streams of air. There is a primary stream and a secondary stream. So secondary stream is used to cool the primary stream, which never comes in direct contact with the water. So here, depending on the efficiency of this is a heat exchanger. Depending on the efficiency, it can bring the temperature. Whatever we get in the direct evaporative cooling, we can get 4 to 5 degree lower than that. And the RH also, there is a very less addition of moisture. And to add to that, it can be further integrated if you want the exact parameters of 25 degrees centigrade or RS less than 60%. Then you can have an additional DX coil or a chill water coil, and you can even get these conditions. So we have if we compare a pre-cooling system, for example, in a hospital, when we are talking of TFAs, it consumes normally 150 CFM per ton it consumes. But if we use a pre-cooling unit with the indirect evaporative cooling, it will, for 1000 CFM, it is around, it will consume around 5.9 TR, whereas this is without the IEC unit, it will be 5.9, and if we employ a IEC unit, it will be 3.8. That means we are saving around 2 tons of air conditioning per 1000 CFM. So this is a substantial saving, because in the hospital, fresh air loads are substantial. So this is the application of the hybrid systems. If we go with the direct, indirect evaporative unit along with the coil, the system can be used in several modes. When the conditions, outside conditions are favorable, you can use in the ventilation mode, only the fresh air can be circulated. When it is a dry area, you can use it as a DEC unit, DEC form. And if in the moderate climate, when moisture is there, relatively there, then we can use it in the IC, indirect evaporative cooling unit type. Then if we want, particularly in the monsoon, and if we want precise conditions, we can add on to a coil and get the IC plus coil. It will be an application, but it will be a once through application, means the total air is exhausted. And then the same unit can also be used with the other units off, and we can only run the DX coil in the certain areas. So like doing all these juggleries, we can use the same unit for different parts of the year and different parts of the day also. Automatically, it can switch over from one system to another. It will also yield around 40% savings as compared to the mechanical air conditioning. Now, what are the potential areas which can be good candidates for the hybrid cooling? They are OPDs, lobbies, reception, waiting areas, kitchen, laundry, physical occupational areas, maintenance departments, parts. All these areas we can safely go for hybrid cooling and save on the energy. Then you have also like natural ventilation, that also has a major part to play in saving the energy. Now, these are the national guidelines for infection prevention control, which have been stipulated, and it says that it is besides the other controls, it is also saying that we should use, it is rather stipulating that natural ventilation, where possible, we should be going for the natural ventilation, because with the natural ventilation, we can not only increase the airflow rates, we can go for the lower capital operation maintenance costs. So without going into all these details, mechanical ventilation, we know it is suitable for all the conditions, but only thing is it is expensive to maintain, and then it can, we can go for a limited air quantity, air changes with this system, whereas with the natural ventilation, it is suitable for the certain climates only. Very cold climates, it may not be effective, or very hot, it will not be effective. And mixed mode ventilation is desirable, where we can go for a mix of the systems. It is more flexible, and it will be suitable for most of the climates and the weather conditions. So the advantages of natural ventilation will be low capital operation and maintenance cost, high ventilation rates possible, whereas disadvantages will be reduced comfort level, directional control will not be possible because it will be depending on the local air currents, and it is also affected by the outdoor climate and the mechanical ventilation. Now coming to natural ventilation techniques. Even WHO has approved different natural ventilation techniques, and they have said that it's very much appropriate for infection control in a healthcare facility. So different configurations for the natural ventilation are your cross flow ventilation, or a wind tower ventilation, or a stack ventilation, or an atrium sort of a thing, where the air, the cold air, the hot air rises and it's displaced, and cold air takes its place. And similarly, in the hybrid ventilation in the mixed part, we can also take help of a fan, which will assist the intake of the cold air inside the building. So this is a fan assisted ventilation. And also then there is a concept of buried pipes, which is now gaining popularity. And we can go, because the temperature under the soil that remains constant throughout the year, and it is 4 to 5 degrees centigrade less than the outside temperature. So we can use that our advantage for natural ventilation. And it's a very interesting fact to see that how much now, why we are not employing, why the designers are not being employing, because we don't go into the details, or we do not want to take risks, and we do not know how it will perform. But if we go in the depth of this, in fact, WHO also, it has given there is a calculation available which tells that, like, with different type of configurations in the opening and the air velocity, how much air changes are guaranteed and what ventilation rates are available. So consider a ward of 7 meter length or 6 meter width and 3 meter height, and which is a window of 1.5 by 2 meter and a door of 1 square meter. Then interestingly, if this complete open window and one open door can yield 37 air changes per hour of the ventilation, which is really, really very amazing, very interesting to find. And then open window 50, if the window is 50% open and the door is fully open, still we get 28 air changes. And with the open window and the completely closed door, we get 4 air changes. And this is a picture depicting the single corridor type of a ventilation pattern. This is a courtyard type ventilation pattern, where here, like how the natural ventilation, it will make the building cool. So this is particularly applicable for the facilities in the smaller cities, or for smaller, or for where the favorable ambient conditions are there, or depending on the size of the facility and the funds of the hospital. If we compare how WHO it rates the various system as per their effectiveness in providing the infection control, then in most of the climates, like hot and dry or moderate climates, the hybrid and mixed mode gets the equal ranking as the mechanical ventilation, whereas only in the cold climates it is getting only the fair ranking, right? Then now coming to displacement ventilation for infection control. Displacement, what is normally conventionally, what is the system? System is that, like, there is a supply from the top, and then there is a lot of mixing. The total recirculation happens and the complete thing gets mixed. So that means the contamination is not getting removed. So it can cause infection. So if we go for a displacement ventilation here, it will ensure that the supply is at a lower temperature and we are picking up the exhaust at a higher level at a low velocity, so that what happens is that all the contaminants are immediately removed from the space. So that's an effective method of infection control also in the healthcare facility. And it's a good candidate in the areas where waiting areas are there, or in the reception where we do not know that the people may be there with infection, and they can cause the infection spread also. There the displacement ventilation is of much advantage. Then coming to humidity management without reheat, that is another method of reducing the power consumption through the face and bypass damper control. Normally what happens is if we are designing an air handling unit for 2000 CFM, it will keep running at 2000 CFM in summer or monsoon, whether the requirement is there or not there, whether the equipment is on or not on. And the conventional way is to provide reheat to prevent the overcooling and to bring back the conditions to normal. But if we use the face and bypass damper control, as we increase the bypass air quantity based on the need, you can bring the RH under control. So here you are seeing that with the 10% bypass or 25% or 50%, we can increase the supply temperature and we can bring the RH under control. So this is a non-mechanical thing, and what will happen is that it can help in reducing the power consumption due to the reheat. Then we have the wraparound heat pipe system also, which can improve the dehumidification facility of the cooling coil, and at the same time, it can eliminate the requirement of heat pipe. So what is a pipe basically? Heat pipes are basically, these are the pipes which carry the refrigerant, and they have three sections. They are wrapped around the cooling coil. This is the suction side and this is the discharge side. Here in the warmer side, the refrigerant that will pick up the heat, it will turn into vapor and it will cool the incoming air by 15 to 20 degrees Fahrenheit. So that the cooling coil, it sees the air at a lower wet bulb and the dehumidification capability of the cooling coil is improved. And then this refrigerant vapor, when it goes to the discharge side, and then again in this section of the heat pipe, it will condense and release the heat. That means it will eliminate the requirement of the reheat. So this is a very, very effective method and it's very common abroad, but there is a cost to it. Normally, people avoid this, but it's a very, very effective method of energy conservation. So this is again repeating the same, so I'm skipping it. So advantages of heat pipes are that heat pipe increases the dehumidification. There is no moving part. It is very energy efficient and it can be effectively applied to the particularly the 100% pressure systems. So this is a thing which shows that how warm and humid this thing, it can be pre-cooled through a heat pipe from 95 to 78 degrees Fahrenheit. And then again, the reheat can be provided by the condensation of the refrigerant in the discharge side, in the condenser side of the heat pipe. Then coming to the energy considerations for architects. Now the building starts with the inception of the architecture, and the architects, they need to keep in mind, the various parameters that go into the improving building envelopes, because it has a major impact in reducing the heat gain in a building throughout the life of the building. And it reduces the requirement of mechanical air conditioning. So now what are these factors? Some factors we'll touch upon, like the orientation of the building. I mean, we can, from these figures, we see that east and west orientation, they get the maximum radiation of sun during the summer. And then it is the southern side, and then it is the northern side. So like while deciding the layout, if possible, as per the site conditions, if the building can be aligned with the shorter side along the east-west axis, it can be a major saving in the heat loads. And similarly, we can reduce the exposed area, because it's from the exposed area only where the solar gain comes into the building envelope. So if we make it more, reduce the exposed area, we can reduce the heat gain into the building. Glazing selection, go for a high efficiency glazing, go for the U values as per ECBC, provide shading devices. You can add insulation to the exposed roofs and walls, U values as per ECBC. So here, in fact, adding insulation may reduce the heat gain from that particular wall by around 80%. And likewise, reduce the exposed area. Instead of making, reduce the perimeter areas can be reduced, internal areas can be increased. Optimum wall window ratio should be given. Again, the guidelines are given in ECBC. Natural lighting should be trapped as far as possible, for particularly for the areas like atriums or canteens and reception. And AEC blocks, they are the green building material with the very low heat induction. So we should use that. The architects should use that. Take advantage of natural ventilation. Try to align the longer side towards the normal air current direction in that prevalent in that area. So it will keep the building naturally cool. Then we come to the cool roofs. Roofs can have reflective colors. Roof insulation is a must. We can go for plantations. We can go for vents to remove the hot air. Control of microclimate, plantation of the trees around the building also, because of the evaporation effect, it will keep the building cool. And greenery also, avoid the hard paving. These are some architectural aspects. And if we decide in the inside areas, we can locate the internal spaces optimally to reduce the internal loads. How it can be done? The spaces with the high internal loads, they should not be located towards the south. And the spaces like stores, circulation areas, they should be located on the east-west axis to provide buffer zones for the internal spaces. And normally what happens is the open workstations, they require low loads than the peripheral areas. The peripheral cabins or the consultant rooms or the chambers, wherever they are required, they should be located towards the north side, and other open areas can be on the other side. And likewise, since the south areas, they will induct more heat from the that direction. So it is always preferable to keep the mechanical equipment rooms on the north side. That will improve the service life. Architects should be generous, should give space for the generous duct sizes. Normally there is always a fight regarding the false ceiling heights, and aspect ratios are not maintained. So that should be taken care of during the design. Space for the rounded transitions. Metering should be provided. There should be ample space for the maintenance in the mechanical room, ceiling shafts, lighting controls, and nowadays, in fact, water cooled imaging equipment is also there. MRI machines and manufacturers, they supply the MRI equipment there with their dedicated chillers. So that should be used. And then the radiant heat. Other strategies for this are the active technologies. Around 32 active technologies today are available. These may be, we can just brief it down to variable chill water pumping, solar energy, energy recovery heat wheels, air side economizers, water side economizers, variable speed cooling tower fan control, low approach cooling towers, high efficiency condensing boilers, boiler economizer, dedicated steam boiler. So in fact, we'll just briefly, very briefly touch upon these. And like variable chill water pumping, we all know it will modulate the chill water as per the cooling load and the demand load, and it can reduce the power consumption by 10 to 15%. Then we have the solar energy. We can harness the solar energy and store it in the PV panels to use it when required. We have the energy recovery heat wheels, wherein we can exchange the heat between the incoming and the return air streams, and it can reduce the load by 50 to 60%. We have the air side economizers. Depending on the ambient conditions, we can go for free cooling, switch off the compressor, or we can go for more of the fresh air. It saves the energy of the chiller. Then likewise, we have a water side economizer. So during winter season or during nighttime operation for certain areas, what can be done is that the cooling tower water, which is at a lower temperature, it can be circulated through a heat exchanger, and on the secondary side, we can run the same water in the chill water coils. So this is called the reverse cycle operation. We can go for modulating control on the cooling tower fans, can be provided with BFDs, and that will save the fan energy. Then we have low approach cooling towers available today with more fill, CTI approval, and CTI certification, which are more efficient and consume less fan power. And high efficiency condensing boilers with a very good combustion efficiency, 88 to 92%. Boiler economizers, the flue gases, we can go for energy recovery from the flue gases through different modes. There can be wraparound coils. And then we should go for, when we are designing for a hospital facility, we should go for separate boilers for heating, humidification. It should not be a centralized heating system because operation times are different and requirements are also different. So there should be a separate thing. And even if it is there are different towers, different blocks in the hospital facility, they should have separate independent hot water generators, because that will reduce the interconnecting piping cost, and it will also reduce the distribution losses. And we should go for high temperature hot water heating system that will reduce the piping cost as well as the pumping cost. And we should also we should use demand. Normally, heating requirements in the hospital are relatively smaller than the cooling. So normally I have not seen that the consultants are specifying variable speed pumping just for the cost savings on the heating systems. But we should go for that, because every drop, it fills the ocean. So we should take advantage of all the opportunities wherever we can go for the energy savings. Plate type air-to-air heat exchangers, wherever we want to recover heat, we should use plate type heat exchangers which have a sensible heat efficiency of 60 to 80%. Heat pipe systems, we already discussed that earlier. And then the run around loop coils to again recover heat from the exhaust streams, because there are so many exhausts which are happening. If we are seeing that we are losing energy in a substantial quantity in any particular exhaust stream, we can use run around loop coils, where a solution of glycol and water that is pumped between the two coils, and we can retrieve the cooling into the incoming supply stream. And then we should also definitely, in fact, we should consider a separate chiller for OT, because OT, as we have seen, that there is a lower requirement of 18 degrees centigrade or 21 degree, and even lower 16 degree also. So it is always advisable to run the chiller, separate chiller for OT, because with the normal chiller, you can always go for a higher temperature set point to conserve energy, but then the OT conditions will not be achievable. So it's advisable to go for a separate chiller for OT, and which can also serve as a winter cooling chiller for the OT and the different areas. Selection of one chiller as heat pump. We have the areas in the hospital which have a simultaneous requirement of heating and cooling. So one chiller can be selected as a heat pump. Variable condenser water pumping and variable primary chill water pumping also have become quite now popular nowadays, and they also help in yielding energy savings. Then we can go for cogeneration systems, wherever in the power plants, we all know that the 70% energy it is wasted as heat in the power plants. So the same heat, the same waste heat can be used in form of absorption chillers for cooling, or it can also be used for heating purposes in the hospital. Thermal storage is a old concept, which is a battery of the charge, like where we can store the cooling during night time and then use it when it is required. Or we can shift the cooling from the high peak period to the low peak time and use it during the daytime. Then geothermal pumps and HVLS fans are also a new concept. And HVLS fans with their 7 feet diameter, very effective, and can be there in the double height waiting areas, can be used. And then the latest technologies are smart control and Internet of Things, which is the fourth industrial revolution. When we talked of the industrial revolutions, first industrial revolution was the advent of steam engine, second was the industrialization, third was digitization, and now is the era of fourth industrial revolution, Industry 4, which calls for inter-IoTs and digital twins, which also will be just touching upon in brief, because it's a topic of great interest nowadays. And then we can go for personalized portable HVAC technologies. Instead of cooling the complete area, we can go for personal stations for ventilation and for air conditioning. Targeting net zero with HVAC modeling and modular HVAC systems also. They enable higher energy efficiency, give flexibility of control, and they can be customized for the specific work areas without affecting the complete area. Then we have so many air purification technologies also in prevalence nowadays in the industry. We have UVGI, PCO, ESP, plasma, nanofiber. So all these technologies are meant for with these any one of these we can reduce the fresh air quantity that is required, and it can be adopted to optimize the indoor air quality, as well as we can reduce the ventilation air quantity with this, and reduce the power consumption which is associated with the fresh air requirement, cooling, and also thus we can reduce the carbon footprint size. Then underfloor cooling, radiant cooling is one application which is again becoming popular. In this, it's a convection cooling system from the floor where chill water pipes are run through the floor, which cool the warm air in the room. Then we have the underfloor plenum, underfloor distribution, where the underfloor plenum only acts as a supplier duct, and the grills will be opened at the workstation areas. So it enables the task ambient conditions, and higher supplier temperatures can be given. So we can run the chillers at higher temperatures, yielding energy savings. Chilled beams are again a concept which is there. We can go for chill water pipes embedded in the beams, or they can be separately hung, and due to convection it cools the air inside the room. Or it can be active or passive. We can have, there are systems in which we have the nozzles which create the negative pressure and induct the air from the room, then to pass it over the chilled water pipes and cool it. So some more recommendations for energy conservation are AHU zoning, then consider separate AHUs for the different departments, use supplemental cooling, recooling coils, use DX recooling coils downstream wherever it is required, and supplemental cooling coils can be served by separate air-cooled chillers, or there can be condensing units also, and suggest the radiology equipment to provide the separate equipment chiller, as I was saying, for the MRI, and the LINAC also. LINAC separate chillers are provided. Size 1 chiller for winter loads. That will be more, it will then run near its peak capacity requirement, and the chillers, the machines always, they are most efficient when they are operated near their peak load conditions. Use the pressure independent valves on the coils, that will reduce the unnecessarily throttling which is required. It will reduce that. Use high delta temperature to reduce the piping and pumping costs. Large AHUs should be used instead of very small AHUs. The ceiling mounted AHUs should not be preferred. And calculate the actual fan static pressures instead of just assuming, to avoid the excessive throttling. Calculate the actual system head, and use the electrostatic filters in kitchen AC. Conventionally, it used to be 100% pressure in the hospitals or in the other hospitality commercial kitchens also. But now it has given way to the latest technology, electrostatic filters, and with the carbon filters, we can go with the kitchen AC with the recirculation methods. So that should be employed. Consider hybrid air conditioning in these areas like lobbies, reception. Consider good insulation material for pipes and ducts. And then very important point, the dead band should be broadened. Where, we start the heating on, heating should not be on when till the temperature drops below 19 degrees centigrade, and the cooling temperature should be on only when the temperature exceeds 24. There should be at least a 5-degree band, dead band, and there should not be an overlap of the heating and cooling systems. And in the ventilation also, use mixed mode ventilation system, and try using localized hoods over the sterilizer equipment and the laundry equipment. Consider heat recovery from kitchen laundry equipments. Provide some meters. That's very important, because until and unless we are monitoring, we are providing meters for monitoring the energy consumption, we cannot take the suitable actions to improve it. Then coming to mitigating system losses, selection of high efficiency equipment. Nowadays, high efficiency chillers are available as good as COP 6.3, and 6.2, and whatever is stipulated in ECBC, we should follow that. We have the chillers which with the VFDs, so they can save up to 30% power saving through better part load operation. We know that like most of the systems, they run only 1% of the times at their full load, and 70% of the time are their part loads only. Magnetic bearings also, they can reduce the losses. And then mitigating system losses by going for energy efficient air handling units, which are low leakages, high efficiency blowers, use VFDs, low leakage dampers, and the optimal phase velocity. We should not try to, smaller the size of the HU by increasing the phase velocity, because that will reduce the performance, and rather, and increase the pressure drop also. So it is advisable wherever we are going for high static pressure, we should go for lower phase velocities. AMCA certified blowers, we should go for heat recovery units also with the AHUs wherever the pressure component is higher. And then mitigating system losses in the high efficiency boiler, try to avoid the electrical boiler, use gas boiler, because that will reduce the power consumption as well as it will reduce the carbon dioxide emissions. High efficiency motor and pumps should be employed. Right size the pumps, trim the impeller instead of modulating the valve. Use variable speed drive, minimize the pressure drop, use very highly efficient seals. So this is the something about the good equipment selection for energy conservation. Then the energy savings by operation, maintenance, testing, balancing. Normally the systems are provided with building automation, and building automation systems really, besides providing sequencing of the equipment, they can also yield energy savings by 8 to 10% through better operation. We should go for the energy management system, remote control and remote monitoring of the HVAC system, and it's a smart management of the system. And nowadays, it's possible, instead of the operator or instead of viewing the equipment from the shop floor, the machine manufacturers, they can monitor as well as control the machines in the all parts of the globe from a single point. So that is a cloud enabled technology, which is the latest. And these systems are definitely costly, but they are very energy efficient, and it's the future for a sustainable hospital. And in the retrofits, we can also say that, duct and coil cleaning is very important to improve the efficiency, because with time and with the scaling, the heat exchange efficiency reduces. So to improve the indoor air quality, go for UV system. It reduces the system maintenance, and it keeps the system operating at a high efficiency for a long time. And if the ductwork redesign may be required at certain places to mitigate the design mistakes, to avoid the hot and cold spots, to avoid the drafts, to improve the poor air quality, we should go for it. At times what I see, that in the renovation jobs, the customers, they do ask us to replace the AHUs. AHUs hamare purane ho gaye hain, they are not performing, but they will never allow to touch the ducting. Because there is a misconception. Misconception is बहुत ज़्यादा मतलब cost है. It is not like that. Though I understand in the running facilities it is difficult, but it is not impossible. It can always be taken in phases, because ductwork, if it is not compatible with the AHU, or the दिन में वैसे इतना scaling हो गया होगा, so much dust and dirt would have accumulated inside. It would be breeding ground for the microbes, algae. So we should try to endeavor, and there can be design mistakes, there can be hot and cold spots if they are there. We should try to analyze that, and if required, we should go for the replacement of the ducting as well. Then likewise, piping redesign may be required if there are design mistakes, if there are not proper water flows coming at the requisite areas, and not getting balanced. We should have a relook in the design, and we should go for the retrofit. Lighting retrofit, again, today smart products are there, occupancy sensors are there, LED lighting is there, which consume much lesser power. So we should think of replacing the old things with the newer technology. So testing and balancing, again, so it's very important. We need to ensure proper balancing. In fact, nowadays, balancing of the water and air flows, normally, it's not undertaken that meticulously because of the volume of the jobs. But it is very, very important. Systems should not be kept unbalanced. Both water side and air side should be properly balanced and got validated. Also, if one has to spend some extra for third party validation, should be done because it has a very early payback. So this is an interesting thing, digital twins, which I was studying upon, and I thought I will include 2-3 slides on in the end on the digital twins technology. So what are digital twins? They are the technology of the fourth industrial revolution. As I mentioned earlier, ones were steam engines, the first revolution, second was the rapid industrialization, third was the automation and the digitalization, and the latest is the Industry 4, where we are talking of digital twins, which is a virtual replica of the physical product, process, or system. And it is, gaining popularity in all the fields of industry, whether it is automotive, manufacturing, and medical. And it bridges the physical and the digital world. It's a total replica of the physical product or a process, as so as to say that, like, in the future we can expect that we will be having the digital twins of ourselves. So how it is applicable, how it is helpful in a hospital? By digitally cloning a hospital, the administrators, doctors and nurses, they can have a real-time insight into the patient health and workflows. They will know how the emergency rooms they are occupied, how the flow can be reduced, how the patient flow can be managed. So that will reduce the operational cost as well as at the same time improve the patient experience. And it's a basically IoT, Internet of Things, with the sensors, and it is collecting data, monitoring, storing in the cloud, and using the past data, and then utilizing that data in the various applications. It can be also, sensors can be used to monitor the patients, coordinate the equipment and staff, and they can be analyzed based on their digital, data of the health condition of the person at a particular time. They can be alerted on the future things which can happen to the person, so that the immediate action is taken and the lifespan of the person can be increased. So blue emergency, so as to say, like, digital replicas, they can be used to predict and prevent the patient emergencies like cardiopulmonary or respiratory arrest, which are the so-called blue emergencies, can result in more lives could be saved. So it's really, really very interesting to know that so much technology enhancement is happening in the industry. And as I said, like, the medical industry is such industry where every day new changes are happening. So new medical equipment or medicines being tried on actual samples. Instead of doing that, it can be a virtual testing which eliminates the human trials during the development phase. So it makes the process cost effective, fast and safe. So this is a trend which is going to be there for sustainability of the hospitals, particularly in the large projects and in the medical industry. So I can say time is not far when we will have virtual version of ourselves, which will be kept up to date with our health condition. So it will run the digital test on the simulations to find potential health problems before they happen. So to conclude, I would say that all these things what we discussed regarding sustainability of the hospitals has to be a joint effort. It cannot be at a single point. All the steps, right from the architects, designers, project management teams, facility owners, they need to be sensitized about the requirement of energy efficiency of the HVAC systems. And rather than considering only the capex, capital cost, we need to give importance to the life cycle costs, safety aspects, sustainability of the planet. So it's always better to consider the life cycle costs as also the environmental concerns, how the systems are lowering the carbon dioxide emissions, how we can reduce the hydrofluorocarbons while improving the system efficiency, because that only can be a way forward for constructing sustainable hospital buildings, and that is how we can preserve our planet for our future generations. So with that, I conclude my presentation. And thank you so much for bearing with me. And we can take up the questions now. I'll just go through. Hello, Tapasji?
Yes, ma'am. Yeah. So should we start the question and answer
We
session?
can start the questions.
Yeah. So I think first question is from Mr. Lawyer. Do you try any technology to remove moisture in hospital, as dehumidifications require a lot of energy, hence alternate method will be desired?
Yeah, we have tried. Like normally, dehumidification is a part of that, and additional supplemental coils are there. Or dehumidifiers also have been used in the moist areas. Dehumidifiers have been used in the OTs. So, and as I said, this heat pipes. We have not in the hospital, but in the other applications, we have in the comfort application, we have tried, and they have been found to be very effective without consuming the energy. So we have tried the heat pipes. I think that answers.
Yeah.
Then second question is how to control pressure quantum in a VAV controlled air systems. So that is a very good question. How to control pressure quantum, because when we are modulating the VAV, automatically the pressure quantum also comes reduced. In fact, there are various 2-3 methods. I will mail that also. We took those these techniques. Either it can be a separate PFA duct which can be run. The pressure system can be separate, which will be not modulated. That will be on all the times. So in fact, if I get the email, I will send you the process diagrams also how to do it in the without compromising on the pressure quantum in the VAV system. So, then the third question is, in hospital, there is huge filtration requirement, and hence lowering air requirement will be more beneficial compared to raising set point. What is your experience of the same? Yes, so that in fact, when I covered in the later part of the presentation, that lowering the air requirement is possible, and particularly during the COVID times, many technologies have come forward. Though ISHRAE is not, favoring, or I mean, it's not saying anything openly, but they're not disputing also the efficacies of these technologies. UV, in fact, has been given a lot of recommendation, and other technologies also are at par. There are technologies like PCO or plasma and all of these things, by way of which, you can reduce the pressure quantum. And there are calculations available in the ISHRAE standard, wherein we can reduce the pressure quantity by employing the filtration technologies and reduce the cost of air conditioning because of the higher pressure requirements, filtration. But the huge filtration requirement, wherever it is coming, there, I mean, filtration has to be there. Like where the ISHRAE stipulates HEPA filters, you have to give. It's only the pressure requirements can be, modulated by providing the different technologies in the filtration, the new technologies which have come in. But wherever MERV 14, 13 filters or MERV 14 are recommended, we need to get that. We cannot do without that. Then the next question is, how does the control of OT or burn unit works in terms maintaining temperature and humidity? How does the control of OT, question is not very clear. How does the control of OT work in terms of maintaining temperature and humidity? These are two separate things, maybe we can say. In the OTs, it is normally, we give controllers which through which the surgeons, they can monitor and even they can control. If they want to change the set points, it is a possibility that they can, within the control provided inside the OT, you can vary the temperature from 17 degrees centigrade to 27 degrees centigrade. It is possible from within the OT if the suitable controls are provided. So likewise, burn units will be separate because they require higher temperature and higher RH. They are also, that unit has to be, HU unit has to be separate. So temperature and humidity have to be maintained according to the specific application in the OT, but the unit and the systems provided will be separate. Next question is, can HMX cooling be used in hot and humid climate like Kolkata? Hot and humid climate like Kolkata, we cannot go for the normal evaporative cooling. We can go for indirect evaporative cooling at certain periods of time, but it has to be a hybrid. If we are talking of the humid places like Mumbai or Kolkata, direct IEC will not be very effective. It has to be augmented with the supplemental DX or the chill water coil, so that during part of the year we can run it on the IEC with the HMX, but during the worst period when there is a lot of humidity, we need to run the coil also along with it. Next question is, hybrid cooling system is good where there is dry summer, but what about areas where RH is high like coastal areas? So that I have already answered, and we showed in the presentation also that we have the supplemental systems. Hybrid cooling is supplemented with the DX or a chill water coil. So during the dry summer, maybe that is not required. We go with only the indirect type evaporative cooling. But when the RH is higher, or where we require precise temperature of 24, 25 and 60% RH, then maybe where we can use the IEC and the chill water coil in unison. So there also we will be saving as compared to the total mechanical refrigeration. There will be around 30 to 40% savings even with the hybrid systems. The next question again is by Mr. Izhar Ahmed, that how natural ventilation works when most of the areas in India are polluted in terms of particulate and gaseous pollutants. So very relevant point. In fact, when we go for natural ventilation in the industrial applications also, where it is only the normal ventilation, we do see that how is the ambient air conditions. If it is, and we take the test readings, that what are the pollutant levels, and where that surrounding area is free of the contaminants, and there are the levels of the particulate and the gaseous pollutants, ambient air quality levels. If the outside area contaminant levels are higher than the threshold, then we need to have the certain filters also in the fresh air. So we can provide MERV filters are required in case the pollutants levels are higher. So that kind of a thing has to be implemented. Next question is, as the heat gain due to radiation is maximum in east and west direction, why the larger axis of the building should be along that? No, actually, what I showed in the presentation was that the shorter dimension should be towards the east and west, not the larger this thing, because the exposed area, if the shorter dimension is facing the east and west, it will have the lower exposure in those directions, and the radiation intake will be less. Other question is, if we use hot water generation from body heat of PV solar panel, then efficiency of PV panel will increase and free hot water available. Can this be tried in hospital? This question is not very clear to me. If we use hot water generation from body heat of PV solar panel, then efficiency of this will increase and free hot water available. I'll revert on this. Why not remote heat pump for hospital against boiler? Yes, that's a very relevant point. Heat pump does make a sense, and we are using heat pumps for hospital against the boiler. But only thing is, we have to see that like the chiller, which is also used as a heat pump, it should have the total feasibility also, whatever is the hot water requirement, it should be able to deliver that, because it can be a maybe a supplemental part. If it is catering, it can cater to the complete requirement of the monsoon reheat or the winter heating. We can go for heat pump only, or otherwise, if there is a shortfall, we'd have to have an additional boiler. How digital twin is different than IoT? In fact, digital twin, IoT is the Internet of Things, and it is in its advanced version only. It's a digital twin. Internet of Things means when we are connecting the things to the internet, and then digital twin is when we are generating based on the data that is picked up by the sensors, monitors, compiled and connected to the internet. And when we are using that compiled data from the past experience, for example, nowadays the systems are there that like with the digital twins, person has arrived at the airport, the hospital would, the hotel would know that the person has arrived, and immediately they will pick up the person, they will send a car to pick him up. So that's because the digital twin has been created. Digital twin means the cloning of the data, and then combining it, utilizing that for the further action. So it's an extension, it's an extension of IoT only. Share the details of VAB. Okay, I will share the details of VAB on this email ID, sure, for sure. What is benchmark power consumption per bed per day in hospital? This I would not be knowing. I would have to check. I will, because this data can come from a hospital only. So we can check it from any hospital I'm working with. So I'll get back to you on this also. Give me your email ID. I will send the data, find it out and send it. So if any other question is there, I'll be pleased to answer it. Any other question?
Might be in chat box, ma'am. Yeah.
Okay, I'll see.
Is it taken, ma'am? Can we keep air above 20 ACPH in ICU, ICCU, or any critical?
Where is that? 1 second.
Chat box.
Can we keep air above 20 ACPH in ICU, ICCU, or any critical area? See, I will answer to that. Actually, whenever we are stipulating or wherever any standard stipulates some pressure quantity or the total air changes, you always notice that there is a word minimum. It always says minimum. It is not stopping you to increase the pressure quantity or increase, because more the air, better it is going to be. But then after all, increasing the air quantity has an implication on the power consumption. So there has to be a balance between the air quantity and the power consumption, and all the standards they have arrived at a certain value. When we say the negative isolation room 12 air changes, so there is a balance which has been arrived at, that with the 12 air changes, it will be optimal to remove the contamination within the acceptable time, and at the same time it will be opt for the power consumption also. So we can always increase, we are not stopped to increase the air quantity. Yeah.
One more question is about, just above, I think, to have written air, to have operation to be reliable, whether any special consideration to be taken while choosing bulk ceiling type. With normal grid ceiling, is it possible maintaining differential pressure properly for reliable operation of return air and supply air both valve system?
Here, so this question, to have returner behavior, this one
exactly.
using to have returner behavior operation. Actually, wherever we talk of to have return air BAV operation to be reliable, whether any special consideration to be taken while choosing false ceiling type. With normal grid ceilings, is it possible to maintain differential pressure properly for a reliable operation of return air and supply air both BAV system? See, always return air ducted system is always preferable for efficiency and for maintaining the differential pressures. But at the same time, if it's a normal ceiling, also airtight, it does work because in the non-critical areas, clients are normally not ready to spend on the return air ducting. So in the non-critical areas we can go, but definitely in the important critical areas like ICUs or operation theaters, where the directional control and the pressure differential, even in the isolation rooms, we need to have the separate return duct. So there the type of false ceiling will not matter. But in the normal areas like imaging, radiology, also we need positive pressure only because we don't want the outside dust to get infiltrated. So there we should see that the false ceiling should be airtight. So their gypsum ceiling is preferable rather than the grid ceiling. Most important thing is that it should be airtight. So that the architects or the civil people, they have to ensure. So that's. Yeah, any other question?
I think all the questions has been well taken. So it was a great session, and I'm also very happy that we have Rajnish Agrawal sir with us. He's the treasurer of Delhi chapter of ISHRAE for the current society here, and he had come out. Even he is in meeting, so we have picked up some time for us for this session. So thank you, sir. So further any delay, I request Agrawal sir to put word of thanks for this session.
Thank you, Tapas. Thank you, everyone present here today. As a treasurer, I would say the assets of Delhi chapter of ISHRAE are not in the bank. The assets are here, who are present here in this program. We have such wonderful people who give knowledge, impart knowledge, like Samta ma'am. She herself is a legend in HVAC industry, and our assets are the 53 participants who joined us today. I could see in the between, I think it went up to 53. And believe me, this is a very good presence because in my experience, knowledge is the most difficult thing to give. Nobody is interested to take knowledge unless he's actually interested. We all went to school, colleges, and we know how much we studied there. And if 53 people are coming in the evening and attending this program, it shows that it's a very successful program. And my heartiest thanks to Samta ma'am. Thank you so much, ma'am, for giving us such a beautiful presentation. I see people are requesting the presentation. We might request you to repeat this once again, probably because many people may not be able to get the notice in time, or they may not be able to make it because of working day. But what I understand today, I was talking to somebody who was very excited and he showed me this webinar pamphlet. He said today there's a very good program being organized by ISHRAE, and Samta ma'am is going to address it. So I smiled. I said, yes, I know it. He said, I have worked with Samta ma'am, and she is an authority on hospital design. I said, of course, I know that also. And so thank you so much, madam, for giving us I have attended this program. Luckily, once earlier, not the same program probably, but a similar program in the Meerut chapter when Madam had presented it there. Yes. So that was again, that was my good luck. I attended that program. And thank you so much, ma'am, for taking out time and giving us your valuable, knowledge which you have gained over the years. And
thank you, Jagdish. Thank you so much for shouting so much praises.
No. And then my special thanks to Sugdha ma'am. I don't know whether Sugdha ma'am is there, but she has taken up this initiative of women in ISHRAE, and of course, we know how important are women in our life, and now we know that they are equally important in our professions, and they are meeting or exceeding the competence levels, and this initiative of women in ISHRAE is targeted to bring out more and more women into ISHRAE. And Sugdha ma'am and her team is doing a great job. Thank you, Sugdha ma'am. And my special thanks to Danfoss for helping us organize this program. And my thanks to all the annual partners who help us to do these programs and to conduct these knowledge sessions throughout the year. And of course, I have to thank all my friends in ISHRAE admin side, starting from Tapas to Purnima, to the entire staff of ISHRAE Delhi chapter. And I hope that we do such wonderful programs week after week, and we make ISHRAE the most vibrant chapter, the Delhi chapter, the most vibrant chapter. Thank you, everyone, all the participants who are present here today, and heartiest thanks to you, ma'am.
Thank you so much. Thank you.
Thank you, sir.
Thank you, Tapas ji.
Thank you, everybody. So with your permission, sir, should we close the session for the day?
Yes.